2018, Paper 1. Question 5. Hydrochloric acid is a strong acid. What's that mean? Completely dissociates in water to form H+ ions. Experiment. I've got 10 centimetre cubed of 0.1 mole per decimetre cubed hydrochloric acid. Straight off to get a mark. Concentration, volume, turn volume into decimetre cubed, work out the number of moles of hydrochloric acid. 0.001035. Similarly, I've got barium hydroxide. Barium hydroxide, I've got a concentration and a volume. Get the volume into decimetre cubed, and for barium hydroxide, work out the number of moles, 0.00375. Barium hydroxide is in group 2, so group 2 hydroxides will react with 2 moles of HCl because it will make BaCl2. 2 plus and Cl is 1 minus. So 2 moles of HCl react with 1 mole of barium hydroxide. So I've got 0.001035 moles of HCl. It's going to react with half the amount of barium hydroxide, 2-to-1 ratio, 0.005175 moles of barium hydroxide. But at the start, there's more moles than that of barium hydroxide, 0.00375 moles of barium hydroxide. So I've got barium hydroxide in excess. Subtract the 2 to work out the number of moles of barium hydroxide in excess, 0.0032325. There's a clue in the question, Kw. Kw is H plus multiplied by OH minus concentration. And it's asking you to work out pH. So it seems sensible that if Kw equals H plus concentration multiplied by OH minus concentration, why have they given you Kw? It's so that you can work out H plus concentration from OH minus concentration. That's what Kw does. So I've got 0.0032325 moles of barium hydroxide. When that dissolves in water, 1 mole of barium hydroxide is going to make 2 moles of OH minus ions, so double it. So the number of moles of OH minus ions is twice when it dissociates. 0.006465 moles of OH minus ions. I've got the total volume now, 10.35 and 25, 35.35, 0.3535 decimetre cubed when divided by 1,000. Concentration, I can now work out is moles divided by volume, 0.182885. I've worked out the concentration of OH minus ions. Great. I've got Kw, I've got OH minus concentration. I can work out the H plus concentration, I can work out pH. 13.09 seems reasonable at high pH for barium hydroxide. Hydroxide is a base after all. If that's in excess, then it's going to have a high pH. 5.3, the reason why water is neutral. Something's neutral if H plus concentration equals OH minus concentration. It's nothing to do with the pH. Identify the oxide that could react with water to form a solution with pH 2. Non-metals, things on the right, the oxides of non-metals like phosphorus and oxygen and chlorine, anything on the right hand side, any oxides, non-metal oxides are acids. You know already that sulfur dioxide causes acid rain. Ethanoic acid, CH3COH, dissociates in water to make H plus ions, as all acids do, and what's left over an ethanoate ion, CH3COO minus. So I've got the concentrations of things on the right hand side divided by the concentrations of things on the left hand side. Great. A buffer solution, 0.25 moles of sodium ethanoate, is dissolved in 500 centimetre cubed, 0.07 mole per decimetre cubed of ethanoic acid. Without going any further, I've got a volume and a concentration of ethanoic acid. Let's get a mark. Concentration moles divided by volume, 0.07 is moles divided by 0.5. Work out the number of moles of ethanoic acid, 0.035. For sodium ethanoate, it's given me the number of moles. I've got the expression Ka, ethanoate ion concentration multiplied by H plus concentration divided by ethanoic acid concentration. For a buffer, you cancel a bracket top and bottom and leave H plus with the brackets round it as a concentration, and I've now then got moles of CH3COO minus, moles of CH3COOH. I'll come to why I've coloured it in red in a minute. Ka is the moles of CH3COO-. The moles of them, it tells me that I've got 0.025 moles. I've put that in. The number of moles of ethanoic acid I've worked out is 0.035. I can work out H plus concentration. I could work out pH from the Ka if I wanted to. However, it's not as easy as that, because it said before you work out pH, something else has happened. 5 centimetre cubed of 2 mole per decimetre cubed hydrochloric acid is added to the buffer, and that's going to mess up our number of moles. What do? Well, we work out the number of moles of hydrochloric acid, 5 centimetre cubed, 2 mole per decimetre cubed. Obviously, we're working out number of moles for another mark, because I've been given a concentration of volume. Get the volume into decimetre cubed, work out the number of moles, 0.01 moles of hydrochloric acid. 0.01 moles of hydrochloric acid have been added to the mixture to mess up that calculation. So, if I add acid, that goes on the bottom, and I subtract it from the top. If acid is added, you add the number of moles to the bottom for a buffer, and you subtract it from the top. 0.025 take away 0.01, because this is an acid being added, gets subtracted from the top, and 0.035 add 0.01 goes on the bottom, because the acid's on the bottom, and I subtract it from the top. Whatever I add onto the bottom, I add onto the top. Incidentally, if sodium hydroxide or a base is added, I add that to the top and subtract from the bottom. It's the other way around. I've now got values. I can work out H plus and I can work out pH. So remember, if you add something like an acid, the number of moles gets added onto the bottom and subtracted from the top. Add some sodium hydroxide, that gets subtracted from the bottom and added to the top. Why is that? Well, the number of moles of ethanoate ions, CH3COO- that I've coloured in red, also equals the number of moles of sodium hydroxide at the start. Now in this question we haven't added sodium hydroxide. There's no sodium hydroxide being added to the mixture. But if there were, the number of moles of ethanoate ions equals the number of moles of sodium hydroxide on the top. It's because, if you wanted to know, the sodium hydroxide reacts with ethanoic acid to make ethanoate ions. It makes sodium ethanoate, and that's why the number of moles of ethanoate ions equal the number of moles of sodium hydroxide. But just remember some simple facts. Buffers cancel a bracket top and bottom, leave H plus concentration. Moles of ethanoate ions on the top, or moles of sodium hydroxide that you've added at the beginning. That's the number for the top. The number of moles of acid is at the bottom. That's the number of moles of acid that are left over if there's some kind of neutralization, if there's some excess. In this case there isn't, but if you have to work out excess because you've added a base to an acid, it's the number of moles of excess acid on the bottom. If then it asks you to recalculate because you've added extra acid, add the extra number of moles of acid onto the bottom, subtract the number of moles from the top, or if you add sodium hydroxide, that gets added to the top and subtracted from the bottom. That's buffers.